Welcome back, everybody. So in this video I want to talk to you about how integrating factors can be used to solve partial differential equations. So specifically first order. So I'm going to consider something similar to what we've done in previous videos, but now I have a CU term here on the left. So now for this technique, the right side does not have to be 0, but to minimize the algebra, I'm going to set the right side 0 just to illustrate the technique. So know that it can be applied to more. It can be applied if this right side is not 0. So yeah, I'm going to start by making the coefficient of one of these derivatives 1. So I'm going to divide both sides by a. So doing that gives me partial v partial of x plus b over a, partial v partial of y, and then plus c over a times u equals 0. So now that the coefficient is 1, I can use an integrating factor I. This is going to be e to the integral of, I'm going to use the coefficient of u here for the integrand, so this is going to be c over a dx, because the coefficient of the x derivative is 1, so I use x here. So if I do this integral, I get e to the cx over a. What I'm going to do now is multiply both sides of this PDE by I, so that will give me e to the cx over a partial v partial of x plus b over a, e to the cx over a partial v partial of y plus c over a e cx over a u equals 0. Alright, so this first term here and the third term here can be written as the derivative of, specifically the x derivative of e to the cx over a times u by the product rule. And what we're left with is just the second term, so plus b over a, e to the cx over a, partial v partial of y equals 0. So because this is a partial derivative with respect to y, x is treated as a constant, so I can bring this exponential function inside the derivative. So this first term here remains unchanged. So I can write the second term as b over a partial v with respect to y of e to the cx over a times u. And the point of writing it like this is that the quantity in both of these parentheses is the same. So I can make a substitution. I can say that v equals e to the cx over a times u. And as a result, this PDE transforms to partial of v partial of x plus b over a partial of v partial of y equals 0. And if I multiply both sides by a, I get the same equation as we considered before. So I can interpret the left side as a dot product of two vectors, one of AB. One is AB and the other is the gradient of u. So that's what the second vector is on the right side, equals 0. So this first vector is my direction vector d, and second vector is the gradient of u. So this is equal to 0 So this indicates that the directional derivative of u in the direction of d is 0, and that means u varies in a direction perpendicular to d. So if I draw this vector AB in the xy plane, it's going to look like this. And so this vector has a rise of b and a run of a. So the slope is b over a. And the vector, or a vector perpendicular to this, will have a slope of the negative reciprocal. So this here is going to be negative a over b. So the run is going to be b, and the rise is going to be negative a. So this vector is b negative a. So uxy equals arbitrary function of this perpendicular vector b comma negative a dotted into the position vector, which in 2 dimensions is just going to be x comma y. Oh, whoops. Yeah, I put u here, but I was just on autopilot. This should be v. So, pardon me. All right, so let's continue. So this here is going to be v. Right. So, all right. So if I do this dot product, I get f of bx minus ay. So I said before that v is e to the cx over a times u, so now that I know what the general solution is, I can plug back in this formula here. So if I do that, I get e to the cx over a times u equals f bx minus ay. And now I'm going to divide both sides by e to the cx over a. So if I do that, I we finally get an answer for uxy that's going to be e to the negative cx over a times the arbitrary function of bx minus ay. So let's go ahead and check with Mathematica to see if this is correct. So let's have it right there. So, okay. U of xy equals minus cx over a f bx minus ay. Alright, and so now, what was my PDE? That was a first derivative of u. Whoops. And now plus b first derivative of u with respect to y. And now plus c let's see if this is equal to 0. Yep, it is. So this is in fact the correct solution. So yeah, in this video we talked about the integrating factors. So we can use those to solve first order PDEs where both a first derivative is present as well as just u.